Okay, so the another property is granular material. Granular materials are very common in the world. They are relatively unusual because many people say that plasmas are the fourth form of matter, and I would argue that powders are better described as the fourth form of matter, because in compression they generally behave like weak solids. They tend to compact up, and they display a load-bearing strength, something you would not see in liquids except through buoyancy. But basically liquids are not generally compressive load-bearing unless you have them in some kind of container. But when you want to pour a powder, and people pour powder in industrial operations, they behave more like a liquid. And of course, powders generally have zero, I would say, but generally very, very low tensile strengths, except if you go into really extreme conditions, which frankly, no. Unless you do some pre-compaction, you find that granular materials do not have much of a tensile behavior, though they do have shear strength. So there is a range of mechanical behaviors of powders which puts them in some place between solids and liquids. So in terms of compaction and ballistics, if you look at the presentation, the third presentation I did on techniques, 2-dimensional and 3-dimensional, you will have seen that I talked about projectiles moving into sand using an image correlation technique, and also a rod being pushed slowly into sand, and the difference between the motion and the mechanical response in both cases. So in this one, I'll talk mainly about the compaction of sand and then some of the extra studies we've done using glass spheres. We'll talk about the effect of moisture or water being added to the sand, and then shock conditions. Now, the last part of the lecture involves using both sand and glass spheres of different sizes to examine compaction behavior, because there are, I believe, details in the low stress compaction of sand dynamically which can be missed if you attempt to do everything just at a high rate. So when we look at powders under shock loading, we'll discover there is quite a bit of literature out there. There are various porous models which give us a prediction of what's happening, but often that's when the volume, the voids, have been compacted. I said eliminated, but compacted to an extent that they no longer produce any difference between that and a effectively solid material. So a lot of the densification processes are ignored, and here we see a graph on the right-hand side, just showing a kind of area with question marks in it, saying there's some kind of densification occurs, really don't know. And then you've got different lines of prediction based upon the initial percentage volume of the solid. So these are kind of models. They've been around for a reasonably long time, reasonably well known. And are they predictive? Up to an extent, but they're not really accurate to say a 5% level. If we look at densification at low stresses, we can think of a number of processes occurring. And here we have a little diagram showing on the left-hand side the grey particles, which are material which has not been subject to any stress. Then when you put on a low stress, you have a kind of rearrangement of the particles. They move relative to one another. They turn. There's rotational energy in the system. Those particles move, rearrange themselves, and end up being slightly more compact. Then you get a region of localized flow where the material is kind of being crushed and moving into, all the voids are being eliminated. That's the brown region. And then the green region shows a region where fundamentally the material is compacted, and it's just bulk deformation from that point forward. And those kind of 4 regions are generally what we would say are what happens in the granular material. However, what you get is that a lot of the models do not have any mention of what's happening in the microstructure of the material. You can do plate impact experiments, and this is some work that was presented in the shock compression to condensed matter meeting in 2011. Put various channels on there and put powders of different initial densities and perform an impact on the powders and measure the particle velocity of the rear of the powder, and from that derive a shock relationship. So one of the key things about a powder is there's significant energy dissipation. You get quite hot material being produced because you've got localized friction between the particles. You have jetting of material within the voids. You've got this energy absorption due to that. And basically, here we see on the pressure density curve, you have a compaction process shown as starting at this density 0, 0, the original density, the compaction process, some kind of strength, a compaction region up to something that's close to a hot, fully dense material. Then upon release, you follow a isentrope and you go down, and there is a lot of residual compaction in the system. And so that area under that pressure density curve is a measure of the energy you have deposited into the system. Hence, the system can get quite hot. Now, if you took just sand, so this is sand with a average particle size of around about 150 to 210 microns, and you pick it up from a beach, civet, etc., and put it into a container and put it under a loading device and do it at very low rates, you will get responses as shown on the left-hand side here. There's a range of initial densities. That was something we did by just tapping the sand to compact it down just under very low loading. So take the sand, just tap it on the laboratory bench, then measure the density. And we could get a range of starting densities. And we loaded it quite gently in terms of pressure. There was no particle fracture involved, and we got a compaction up to a region of around about 1.650, 1,700 kilograms per meter cubed. You can see that the initial densities gradually move together. There's a fair degree of compaction occurring, but ultimately things are following fairly parallel lines, aiming towards some kind of mass density. So that was okay. That was mainly dry sand. Then we repeated those experiments using sand to which we had added by volume different amounts of water, either dry sand, either 10% water, either 5% water. And here we see the effects of doing that experiment on the drop weight. What we see again is a increase in density. You can see that the dry sand's gone from 1400 to around about 1600, hasn't gone quite as dense. You can see adding the water to the system has provided some lubrication to the system, so you get a good deal more densification under these drop weight conditions. But fundamentally, the kind of response you get is very similar to the low density compaction, but the lubrication of the water has allowed some compaction. We recovered again the sand from that condition, and we discovered there was limited particle fracture. So energy being dissipated through particle fracture was not really a significant process in this condition. Mainly rearrangement of particles within the bed was the main thing. Now, if you revisited the data for, say, uh, low rates, adding the water, you can get this kind of response. And again, just showing this graph to say that once you lubricate those crystals by having a little bit of water present, you can get a whole lot more compaction going on, as is shown here, where the dry material is going in the red lines and it's fairly flat, whereas the moistened material shows significant density increase. Okay, so far reasonably okay, but can we go to higher rates? So here we did some research that was funded through Kinetic, through a research organization in the UK, and we did split Hopkinson pressure bars on sand. Now, for sand, it's obviously a porous material. You cannot just put it between two Hopkinson bars because it will fall out of the way. So you put a jacket around the Hopkinson bar sample, around the rods, and you measure the strain in that jacket. So you need this jacket with a strain gauge on it, and you put the sample within in that jacket, and you use a compaction pulse through the Hopkinson bar, and you'll measure the component of the stress along the bars, sigma x, using the strain gauges on the bars, and you will measure the radial stress, sigma r, by using a formula due to Timoshenko to relate the strain on the outside of that jacket compared to the strain on the inside of the jacket. Because of the size of the thickness of the jacket, you can make a reasonable assumption, do the modeling as well if you so desire, that the time resolution of the strain gauge compared to the time it takes the stress to equilibrate in the jacket, the strain gauge is basically very slow compared to the time resolution of the stress within the jacket. Therefore, you can use the strain on the outer surface in order to get a good measure of the strain on the the stress on the inner surface of the jacket. And this is the kind of data you can obtain from a Hopkinson pressure bar, showing the stress. In case, put it in megapascals. You can see that the axial stress, or the stress along the rod, gets up to be quite high, kind of 500 megapascals. The radial stress we measure follows a very similar behavior, but it's radial stress, so it doesn't go as high in terms of the levels there, only to about 130 megapascals. If you said, well, what is the average pressure in the system? You would do a weighted average along the axial stress and the radial stress and come up with the average pressure. This is a response. You can repeat it with different degrees of water being added, with different particle sizes, etc., and get a series of responses. You can then take your sample arrangement for shock impact, and here we have a system where we have a copper holder with a 3 millimeter thick layer of sand in it, and we're striking it by a plate impactor coming in at up to several hundred meters per second. It hits the front of the target, and we have manganese stress gauges, which I mentioned in tutorial 2, to record the stress in the direction of impact before the sand layer and after the sand layer. And this is the output we got from the rear gauge. So on the front gauge, you measure the input pulse from the copper on copper impact. That's a very generally square kind of pulse. You then have a reflection from the sand layer, coming back to that gauge, and then you measure what goes through the system. Now, because we know the dimensions here and they are consistent from experiment to experiment, we can do a calculation based on time of impact. Sorry, time of stress arriving at the front gauge, time of stress arriving at the rear gauge. And this is what you get for different impact velocities, ranging from a couple of 100 meters a second up to 900 meters per second. And there are, as you can see here, of the order of 5 experiments. The main thing you'll notice is the first thing is the time of arrival of that stress pulse of the system varies quite strongly. It's systematic, but there is a very large change going from around about 4 microseconds to kind of 2.2 microseconds. So what we're saying is the transit time through that sand layer has reduced very much over that process. The other thing you will notice is there is a step followed by a second ramp, and you will notice there is some evolution of smaller features that you see on that ramp. I personally think this is due to the time taken for individual grains to fracture. However, there is no definitive conclusion on that. So, shock and impact in granular materials extensively investigated. We reported this at shock compression condensed matter for a number of years. We also calculated the pressures for the fracture of sand to be about individual grains would fracture around about 200 megapascals. But please remember, a grain in the bed can actually rotate and translate as well as fracture. So there are a number of potential processes that can occur. One thing that we found particularly interesting for the shock response of granular materials was that if we looked at shock particle velocity space, we discovered that having dry sand, and here it is using the black squares, you have a line which is fairly flat compared to other systems you can find, and then adding 10% water, so the white squares there basically had very little difference to the shock compression of the material. When you got to 20% saturation, so this is the white circles there, you can see you had a marked difference there. There's definitely made a difference. But then if you added just a little bit extra water, so 22% saturation instead of 20%, you could have a quite marked difference in the shock response. So what this is indicating is that in the initial part, when you replace the voids with water, you have very little effect initially, but as you get towards filling the majority of the voids, very small variations at that point make a large difference in the shock response of the system. Okay, now one calculation you can do is to try and think about the what's happening on the grain size response compared to the global shock response. So what is the rise time of that first pulse, this pulse, through the system compared to the size of the particles? Under 200 meters a second, you can compare the 1 microsecond rise time against a particle against a shock speed of around about 1 kilometer per second. And what this means is that rise time represents a size of 1 millimeter or 4 grain particles. 500, you're now down to 0.7 of a millimeter or 3 grain particles approximately. And then when you go to 800 meters a second, you've got 2 grain particles between being undisturbed compared to being fully compacted. This shows that there's a doubling effectively of the compaction in the compaction space in the system. So you've got this far more violent process occurring. If you take the shock pressure and you combine it with the results from the Quasi-static bar or the Hopkinson Pressure Bar, what we have here is the results from the Hopkinson Pressure Bar down here. you have the response of the shock experiments at these points. So we were able to have a good overlap in stress in the system. And we compared that to the strain in the system. And again, you could do the pressure calculations if you assumed that the effectively the Poisson's ratio or the lateral thrust of the system was maintained in the same level of relationship as was seen in the Hopkinson bar. And you find that there is a curve to which the sand, on which this particular sand sits, and it's one continuous curve. So you'll see a continual behavior. There's no sudden change in the dynamic regime. It's all fitting onto one curve. So having identified that one of the main differences is in the initial compaction, we decided to follow this up by doing some studies involving sand, but also spheres. So what we have in this example here is showing a spheres of different sizes that we purchased. So these are glass spheres, and you can see them in the green region, the blue region, the orange region, an idea of the particle size distribution. You'll also see behind these much larger, longer areas, and these are due to the sand. So we have, a reasonable amount there. So you've got these polydispersed systems, and you've got these systems. So we use these particular type of analysis to get it. And here we have an example of scanning electron microscopy of the glass spheres, one of the particular batches, and also of the sand. So you can have a comparison of what they look like. Now, we started initially doing some quasi-static compaction experiments, and there are a number of ways of doing this. But what we particularly did was mount a system where we could measure the force applied along the direction of loading to the sand, but also by having a collar with an instrumented load cell down below, we could measure the force that was being transmitted to the outer side of the loading chamber. So effectively, we're removing the effects of wall friction from the system or reducing them very significantly. We can also know about the mechanical properties of this jacket. Again, we can measure the strain on that jacket as well. So we can get a good measure of the components of loading of the system. So we can measure compaction. We can also include lateral expansion as well and lateral friction. What you do find is doing these kind of experiments that up to 40% of the load that you're applying does not particularly go into the sand. A good 40% of that load will actually go into the walls of the container. So this makes a significant difference to the analysis of the results. So you can do a series of experiments using different particle sizes, and here is sand. Here is all the data put onto the same kind of curves, and so basically increasing strength with decreasing particle size in terms of the particles present. That's not a big surprise. You find that kind of analysis in many of the textbooks because critical floor size, the number of floors in these particles, etc., changes with dimension. You can have a particle that is so small it cannot break because using the Griffiths criteria, you find that you cannot get enough energy back to support that crack. Microspheres showed increasing strength with size. More energy was observed in the compaction with smaller particles. Sand, basically, there was no real transition seen in the sand samples. So it just started compacting from the beginning. And there was no stress, no trend in stress required to achieve full compaction in the systems. But porosity was present in all of these samples. So you can do the work on the spheres and find that yes, you have to reach critical level to get the spheres to compact, and they're stronger as they're smaller. With sand, you start getting compaction at very low stresses, and it kind of goes. We recovered the samples and basically discovered, and here you can see a line here amongst these pictures, this sigma p. Basically, this is the stress at which we saw fracture in the spheres, and we're always getting fracture in sand here, so that's why I've got this dotted line. But you can see very clearly there is a kind of stress at which the spheres fracture quite strongly. It's at a certain level. So smaller grain size particles are stronger in terms of their initial mechanical response. However, because we're dealing with the same material, they will ultimately fracture, and in this range of conditions, they started fracturing at the same level. So how does that play? So from this, we get the idea that with the glass spheres, we have a range of compaction behaviors, and we also know when particle fragmentation becomes important. So there are different ways of these particles fracturing. There's rubbing of particles against one another, which causes a small amount of dust to be produced. There is removing of larger amounts of material from the outside of the particle. And then finally, there is just particles breaking into fairly large chunks. So you can find again, there is a fracture strain rate dependence on the amount of each of these you see. When we did shock compaction experiments, our initial ones were looking predominantly at the global shock response, trying to determine the Hugonio of the material. Here, we're doing some experiments. You'll notice instead of a copper container, we have a perspex, we have a lucite, a plexiglass container, and we are impacting at lower velocities, lower stresses in the system, and we're looking for better time resolution in the gauges. And here we have a kind of typical response to the system. Here is the front gauge, kind of loading pulse you see. You'll see some partial release due to reflection of the shock wave from the layer of granular material. And on the rear, you'll see a compaction wave, a precursor wave, followed by the main front. So you'll see this initial step function here. So we could follow this with particle size and grain size. And this is what we found. So if you start with the pulses, you've got 0.37 GPa pulse. You'll see again the surrounding behavior second step, and it will gradually straighten up to become a very thick, very rapid rise in the stress regime. So you can see at what stresses the compaction behavior becomes less important, and fragmentation and fracturing of the grains becomes a significant process. Now, as you change the bed thickness, you can find how the compaction wave, this initial precursor wave, sorry, goes ahead of the material, and you can find its velocity. So here we have, at this particular stress, a couple of stress pulses for different thicknesses of bed, and this is compared. Again, different stress, different bed thicknesses, again showing them compared, and then at a different stress, again, very little change above 1.5 gigapascals. So this compaction behavior is in the region of 0 to 1.5 GPa. If you say, well, what about the effective particle size? What we see here is the comparison of different particle sizes, and you can see the general change amongst the class of materials. 63 micron, basically 63 micron. Basically, not very much changes. 200 micron, very marked change. 600 micron, really clear change in the setup of the system. So that's important. Up here, you'll see these various classes of material compared, and you'll see how they generally collapse onto one type of curve. So this is kind of something we're still interested in looking at. Can we look with by dispersed material, looking at the systems we've got more reduced porosity to start with, see if it's particle size or pore size dependent. What is the controlling factor here? This is again more detail on the shock response of those systems, looking, extending that graph so you can actually see the raw data as it emerges from the system. So from this, we can start looking at shock compaction curves. It is, there are different levels of difficulty of analysis you can undertake in these kind of systems. So we use a linear fit in the first case just to help us in the system. We know there is a double jump in the system, so hence we have this particular line here because we know when that jump occurred from the traces. We can then work back into developing compaction curves, and what we have here is this initial change followed by the compaction. And again, we find that the precursor wave we've been inferred by the initial jump. The magnitude of that wave increased with decreasing particle size. Microsphere curves intersected the porous Hugonios of the calculated for the fully dense material, and we found no measurable precursor wave in sand. So basically, we could compare pilot data onto a comparison with the fully dense material. And for the spheres, you can see that you get quite a good level of agreement between the low-level compactions and the dynamic compaction heading towards this dense response. But with the sand, here is the fully dense response. Here is the Brown et al. Data from 2007, and here we have our data as well. And what we find is, well, here's our shock data, here's our quasi-static data, and here is on the system, and here is the theoretical porous Hugonio curve. So glass spheres, because of their nice shape, because of their consistent packing, etc., show really consistent behavior. The sand really doesn't fit into these simple models at all. You hit the sand hard, you will get a response which is stronger, shall I say, than what you see if you deform it gently and slowly. Again, I think it's to do with the range of particle fracture times in the system. So the conclusions here in the compaction is the compaction response is affected by particle size. Beds of smaller materials have an increased macroscale strength due to the number of load carrying contacts at the boundary. The compaction wave is affected by particle size. The duration and the features you see are quite clearly marked. So the particle elastic limit, so the fact that the spheres have some initial strength produces a precursor feature. The compaction is fracture dominated and heavily dependent on particle morphology and floor density. So beds of a nice regularly shaped particles, you need a lot of energy to get fracture to occur, and it all tends to occur at the same time. Whereas if you've got irregular beds, you can get some localized fracture occurring in individual grains, and so you've got a more gradual change in the process. So there is an agreement between low and high strain rate loading for spherical glass particles But when you get onto irregularly shaped sand with all its flaws and particle sizes, no, there's dynamic only processes that appear to be occurring. So what we have is a fairly complex situation where particle size, flow density, particle shape, and packing all are quite significant. And then if you want to add some water in there, you will get some extra response as well. So that is why granular materials are quite extensively studied and also quite difficult to come up with a consistent theory for polydispersed granular particles. If you can keep the granular particles about the same size, life is generally more straightforward. Okay. Now, the last thing I just want to mention here is one of the things I was doing at one point was looking at very low density silica dust. This is silica dust, which is round about 5% of the theoretical maximum density. So it's extremely porous. This is the kind of glass spheres, basically empty glass spheres is the best way to describe them. Very dusty, very low particle size. And here we show the low rate compaction, where you're starting at very low density and up it goes round about 1400 or so kilograms per meter cubed. Compare that to the sand I talked about earlier, which has a particle size of 150 to 210 microns, and basically was round about 40% porous. So this one here is 95% porous. This one here is 40% porous. Okay, so your initial density that you start at is quite high, 1400 kilograms per meter cube. Here it's 50. And you all kind of go up to round about 1600, 1700. Here, pressing it at 1 gigapascal pressure, you're getting to 1300. You're kind of not even on the scale here. So this shows some of the difficulty in the system dealing with very large differences in theoretical maximum density. If you try and work out a Hugonio from this, and this is one of my favorite curves because it shows me going not really thinking too clearly at the time as I did this analysis. Shock velocity versus particle velocity. So here is the shock velocity predicted from my gauges. Seems like a quite nice straight line. Here's the particle velocity. Now, what you will notice here is that the slope. If I look here, I see 0.4 seems to be about 0.3 here. And actually, if I draw a line from 0, 0 up to this point here, I will get fairly close to all of that data point. So in fact, it's not showing a detached shock wave. What it's showing is the particle velocity and the stress, or the shock velocity, if you want to call it that, are basically the same. So I'm not measuring a shock, I'm measuring a compaction wave. So this response here is basically just compaction, even though the velocities, the particle velocities are very high. That just shows a simple line of what I'm doing, the shock velocity versus particle velocity 1-to-1. And there is a small offset, and I would argue it with that saying there is a small amount of heating occurring in the system. And yes, there is a small amount of energy therefore being placed into that compaction wave, and that's causing a mild increase in stress in the system compared to pure isothermal compaction. But again, the differences we're talking here are fairly small on the grand scheme of things. So if you go to really low density porous materials, you may find they cannot support a shock wave, even if you're going at 1 kilometer a second particle velocity. So that's, again, a quite interesting change in behavior. So here we have the kind of challenges on granular materials, the need to define the starting conditions. What is the defining characteristic? we can do some physical understanding. We can go with approximate behavior. We can look at natural materials, constructed materials. What is the required output? Are we going for an engineering solution where we need something that works? That's important. Are we going for a science solution where we want to understand all the processes occurring? Well, that's important as well. What is the thing that's driving us? There are many ways of doing this, but it would be really good if we could define something simple about particle size distribution or morphology or the number of contact points a particle has in order to get a list of key parameters that we can understand. Compared to other talks, the talk I've given today has a lot of fairly big unanswered questions, because that is the state of our understanding. There's always research going on, advances are being made, but if you said, is there at this moment in time a grand theory where we can define things and make a good prediction? I'll say there are some good engineering models, and we can come up with approximate solutions. But in the area dominated by compaction, there is no single law that's available. Now, Oleg mentioned in the first tutorial the Spiegel-Grady relationship, where its strain rate to the power 4 is linked to stress. For granular materials, that power law is about 2.5. So strain rate to the 2.5 is proportional to the stress in the system. So that's a key thing. So that is the end of this particular presentation, and thank you. I shall now stop sharing the screen and go back to the live, and I'm happy to take questions about the granular material. Unlike previous ones, I personally have a lot of unanswered questions in this area, so I can provide some guidance, I hope. But happy to take those questions, and then after those questions, I'll do my quick addendum to my previous tutorial, lecture 4, because there was a question there which I thought deserved more attention. Hey, Oleg, over to you.
Dear Bill, thank you very much for very nice talk and information that is extremely interesting for us. Please, colleagues, lecture of Professor Proud is open for discussion. Please, questions.
Okay, thank you for the presentation. And maybe I ask some little question. Due to the saturation effect, should we see the different behavior of compacted material and not compacted?
Yeah, for sure. So if you can at the moment you can get rid for glass spheres. At the moment, you can get rid of the vast amount of the porosity of the system, so you can do the compaction. All of those curves tend to reduce onto the same response. The exact level of stress is a little bit dependent upon particle size. Basically, it's the same behavior. When you go to sand, even though it's the same material, it's got a range of particle sizes, because other modes of rearrangement are open to the system, then you get this quite marked behavior. Now, the one thing I didn't mention in the talk is the things called rattlers. So a rattler is where you've got these big particles, and in the bottom of that void between those big particles, you've got a small particle. That small particle sits inside that void, and it's called a rattler because if you shook it, then it would bounce around and make a rattling noise. The thing is, as you compact that polydispersed material, those big particles, for sure, they change their degree of contact. But all of a sudden, you get to the point where that small particle now starts to interact, and the number of points of contact has changed during the compaction. And I think, but I don't know, but you'd have to do some modeling. That would be interesting. What happens when all of a sudden those extra small particles become involved in that compaction process? is that the thing that's having a big effect? That's, I think that's where I'm kind of going with that answer. Does that help you, Yuri? I hope I understood your question.
Yes, yes, I see. I agree with you.
Okay. Okay.
Thank you.
Thank you.
Colleagues, please, questions. Let me continue, Bill. I think granular materials, it's very attractive case for both experimental theoretical study to investigate transition from liquid to solid states. And my question is related to the following. As you know very good, for instance, dusty plasma, it's very good example if we need to consider transition from solid to liquid response, for instance, in shock, due to the variation of the Coulomb interaction. Yes?
Yeah.
And as you know, it's very exciting example when we have dusty plasma crystals and so on, just due to the Coulomb interaction variations. And if we are talking about granular media, what is the key parameters that could provide for the fixed intensity loading transition from quasi-liquid to quasi-solid states according to your experience?
Yeah, exactly. Yeah. Because when you look at the low density silica dust, you see something which is effectively not a very good stress transmission system. So ultimately, the response never reaches the level of anything other than very dusty, low density material with there's compaction occurring, but it never gets to the point of having anything that we define as a kind of elastic precursor or strength term. It's just straightforward compaction. Whereas when you go to something with obviously between 95% porosity and 40% porosity, there's a very big change there. But when you get to 40% porosity, you can clearly see there are precursor waves in the system associated with rearrangement and fracture and the initial compaction of the system, followed by the very aggressive compaction of the system. So there is this transition in behavior. I've seen 5%, which is one extreme, and 40%, which is fairly normal. A lot of our studies in these materials are round about 40% porosity, because with the best will in our world, our particles tend to have a somewhat spherical or ellipsoidal shape, and that means that we will ultimately end up with a certain porous fraction. But if we can change that, if we can control that, and with 3D printing and additive manufacture, we can produce these polydispersed systems with a range of voids in them. I think that provides a way to access these rather strange behaviors. Anyway, so that would be a thing that would I think deserve better attention. Oleg, do you think it's okay if I do the material I have from the fourth lecture? The addendum. Is that okay now? Do you think?
Yes, it's okay.
Okay, right, because I wanted to present this mainly because, as I said, I wanted to make sure that I answered the question from the last lecture in what I hope is a reasonably good way. So again, it's another PowerPoint presentation. What a surprise! But the question that was asked was, I was doing digital image correlation upon a disk of material in the Hopkinson bar. The question was, well, you've got these flow lines, and you've spent some time talking about the effects of porosity, the effects of particle size in these polymer bonded systems. I thought that required a little bit more of of an explanation. So this is work that myself and David Williamson presented in 2009. So for me, it was yesterday, but to everybody else, it was 12 years ago. So the Brazilian test, tensile failure through compression in a predictable location. So there are the anvils, and there's the load being applied and the lateral motion of the anvils. And you get tensile failure in the center there. And these are the controlling relationship. You can look up you can develop a stress map of the system, and here's the equations again. You can do the calculations of it. There is a reference down below, give you an idea of where you can get the full derivation from. And if you do that, you can get the strain distributions in terms of the compressive strain, like this in the system, in terms of the tensile components in the system. And here we can see the region in the middle, and then you can get the shear distributions in the system, and you can have that kind of response. So this assumes a fully homogeneous system, and these are the kind of strains we expect to see. So we did an experiment, and this is that shows the actual setup. Here's the camera. Here is the sample. Here is the support around it. So it's a very large loading structure. And this shroud had liquid and nitrogen cooling in it, and we had so this insulated little tub here, which I hope is fairly clear. And we had a camera to do the high-speed photography. So this is the results at room temperature. Basically, what we have on the left-hand side here is the initial sample, and there was progressive failure at around 107 newtons applied force in the system. So that was the results at room temperature. When we looked at -94, this is the sample there, and there you can see some cracks which appeared suddenly, so catastrophically, at the at 589 newtons. So we did the image correlation analysis, finding that correlation peak. Again, you've seen this particular image a fair few times now. And we can build up the displacement field. So this is the response we got in terms of tensile behavior in the material. So you can see a kind of general shape in the system. So I'll play that again. This is the shear in the system, and we can see the lobes there. So play that again. Now you can see that this is not as nice, not as perfect as the calculation, and I fully agree. The system here was how close was it to the system. So here we have the room temperature response of that material versus the -94 response. You see below that glass transition temperature, you can see the increased strength in the system, the catastrophic failure. And when you look at the failure in the system, this granular composite, when you look in detail, you see this these cracks going kind of around things there quite clearly. And when you do that -94, well, that crack just goes straight through the material. Now, one of the things that we think will be interesting to follow up on this system, but we did not do it at the time, was to look at those deformation maps and see how much they varied statistically from the perfect homogeneous material and how that changed with temperature. That would be an interesting study, because it would show the effect of the microstructure and the microstructural failure process, this versus that, on a much more global scale in the response of the system. So this is why we use in our studies a kind of homogeneous style of model using temperature time superposition for the polymer bonded systems in the region where the system's undergoing bulk deformation, bulk motion, and we can get a very good agreement across strain rates. However, when damage starts occurring, we do get that very local response, that localization of failure. So we're comparing that ideal homogeneous response to a real composite material, but when damage occurs, that's where we really need the development. The other thing is of course, I'll stop sharing the screen here, is the fact that when we get that localization, we do get that very strong microstructural effect, and we need to understand that in greater depth. Okay, so that's what I want to say. Obviously, implied there was differences at the mesoscale level, yet still use a homogeneous style approach to it. This is kind of showing when we transition between the two. But again, looking at the effects of particle size in these composite systems and with temperature, and looking at how much the variation is between a homogeneous material and our real material with temperature, I think that will be an interesting thing. It might even show something linked to the damage process. But okay, there you go. That's kind of
okay.
Okay. Any particular additional information? I'm happy to take questions.
Okay, thank you, Bill, for your very interesting comments. Colleagues, please questions more. Let me please continue when our colleagues are thinking concerning possible questions. Bill, we are involved in a joint project with one of the greatest Russian gas oil company, so-called Gazpromneft. It's the greatest, yes. And the subject of this project it's optimization of the processes of drilling. Yes, due to the study of the interaction of the bore with the rocks, from point of view of fragmentation.
Yeah.
Because the interaction is very close to dynamic.
Yes.
And fracturing, it's very important for to get the gas or oil from the rocks, as you understand. And concerning that, we tried to use our really fundamental results due to the study of fragmentations. It was in situ experiment when we studied dynamic loading of ceramic materials and and also glass. During in situ experiment by dynamic loading and fracture luminescence framing.
Okay.
Okay, and in recovery conditions, because it was interesting for us very much, the statistical distribution, both fragments and time between peaks in fracture luminescence signals. And we found the following, that depending on the density or intensity of loading, the statistical fragmentation, both in fragments and spacing in time between fracture luminescence signals, reveal exponential or power law. It means that for instance, when we have the power law, it means that the process of fragmentation has very pronounced chain properties. You see? Because started from micro level, instantaneously could expand up to the larger scales and so on, in self-keeping regions. And now we are continuing this research. And we are trying to develop two kinds of the laboratory test. It's so-called punch penetration test.
Yeah.
It is the interaction of punch with the rocks, with registration of stress history and the following fragmentation and possible also fracture luminescence, and so-called scratch test.
Yeah.
Yes. Both to extract the information concerning fragmentation statistics in temporal and spatial scales. And I have the feeling that we could combine maybe during this project or in future extend our interest concerning combining of this kind of the research. Yes, because it's the area of very similar strain rate, and the behavior of these materials is very close to granular materials, as you understand.
Yeah. I think there is certainly it would be possible to do some studies where we produce our own, say, sandstone or concrete style material, have some doping in it, and then undertake drilling operations through that material, and vary the strength of the material in a coherent, in a consistent way to understand the effect of pre-damage. Because because drilling is obviously very important, and then people put those perforator charges out to the side of the hole in order to get the movement of the oil and the water into the bore.
Denise, we have the problem with translation.
Я боюсь, Денис отключился. У него сейчас продумал там.
Юр, надо бы как-то восстановить все это дело.
Say hello. Hi there.
Yes, we hear you.
Yeah,
but
I've turned off the camera because something seemed to go along with the connection there. So so basically, yeah, I think that's an important. I think it would be an interesting thing to do, because we can look at the material, the kind of sandstone, for example, the behaviour rock, and again we can make simulants of that rock in a relatively straightforward fashion, and we could look at its mechanical performance under a range of loading conditions, from shock to with Hopkinson Pressure Bar. We have a reasonable degree of expertise in that, so yeah, that would be something to link up on. Absolutely.
And may I ask my colleagues, Irina particularly, Irina, would you please to collect some papers related to a dynamic test for ceramics and fused quartz combined with fragmentation analysis and fracture luminescence statistics for, in English, of course, for Professor Proud, and also just months ago, maybe, we have finished and we have one paper published concerning the processing of DIC images.
Okay.
DIC images in very specific way, Bill, because, for instance, when we have the DIC pattern, in situ loading materials, the field of the strain at the surface contains, of course, some part of deformation strains related to the part of damage. Okay, and the goal of this processing was to investigate the fluctuation dynamics, because fluctuation dynamics, of course, due to the non-linearity of damage kinetics, due to the free energy release, could be very, very pronounced. And we found, for instance, for quasi-static loading, metals and also for composite materials, the separation of dynamics. For instance, in the presence of the notch.
Mhm.
In the presence of the notch. In the presence of the notch, we have in the face portraits for DIC images fluctuations, two types of attractors. The first related to stress distribution in terms of the stress intensity factor. And the second one is related to collective behavior of damaged areas. You see, it's very interesting pattern because we have two clouds of the points on the face portraits, stress rate versus stress. And I think that this kind of because it's the processing of DIC data, I think we could extend this method of the processing also for dynamic loading and maybe for shock loading, Bill. It's really our original method of the processing that we introduced due to the understanding what possible scenario of fluctuation dynamics. And I think we could think concerning processing of different data. And also this paper in English that was published in Structural Integrity Proceedings, we will send you also soon. And if you will have time, we will be very appreciative for your comments.
Okay, great. No, that would be fantastic. I look forward to reading those papers, seeing in more detail what you're doing. But certainly, I would say notch testing in these materials is yet another area. Even when you read ceramic notch tests,
okay,
the American standards for ceramic testing, they do notch tests, but they find just experimental things like using a razor blade or a really sharp metal surface. You have to scratch down the notch in order to get reproducible results, and that's because they need to put in some very precise initial micro damage into the notch in the specimen. So I think those type of variations are quite important to understand. So yeah, absolutely, that sounds like a good thing to do. Yeah.
Bill, you're talking about experiment by Rob Ritchie, something like that?
Yeah, well, actually, the American for ceramics testing, the American Ceramic Society has a series of standard tests. It says, these are the tests that we recognise as giving useful mechanical properties of ceramics, and one of them is a notch test.
Okay.
And you have to make your ceramic with a notch in it, which can be difficult, because generally you cannot machine it. You have to manufacture it like that. But having got that notch into your sample, you then have to do an extra cutting process in order to introduce a good starting point to get a consistent fracture result. Otherwise, the data is very highly scattered. Now, for the American Ceramic Society, this is a way of getting a fracture energy from the system. But from an experimental viewpoint, what they're doing is they're introducing some micro damage, which allows the fracture to nucleate in a consistent fashion in order to get their consistent data. So I think that is the kind of area where certainly attention needs to be paid, because there is a lot of data out there based upon these type of tests where the sample has been preconditioned to fail in a certain way that it probably would not do naturally. The real world is going to be not scratching the surface. It's going to be, what is the material behaving like? You break it, it'll break in different ways. So what I'm saying is, I'll be very interesting to read those read those papers to see if there's anything I can contribute. That'd be good.
Okay, it's very interesting. And just shortly coming back, this in situ test combined with concerning fragmentation, with spatial temporal recording of fragmentation statistic and spacing between time of the peaks, I think it could be interesting from point of view of the estimation of dissipation capacity of ceramics. Yeah. Because you see the quasi-static test practically impossible, for ceramics. I think we could think about this together also.
Yeah, I mean, ceramics are dominated by very high sound speeds generally, and very significant fracture energy. So yeah, so I think that is something for sure. Okay,
Okay.
great.
Okay.
So tomorrow I'll talk about flow of gas
Mhm.
through granular systems, and then start introducing some information on damage to composite systems like concrete ceramics. But that's for tomorrow. Can I thank everybody for listening today, and speak to you very soon.
Yes, Bill, cordially thankful for
Thank you.
all our team.
Thank
All
you.
the
Okay.
best. To be
Thank
clear.
you. Bye bye.